Welcome to the deep dive. Today we are opening a file that, honestly, it feels almost dangerous to talk about.
It really does. We're looking at what some call the most world-changing invention, maybe ever, and also the most fiercely attacked.
We are talking about the $20 billion lie, right?
Absolutely. It's about the vast sums, decades of research poured into conventional hot fusion, trying to build a miniature sun here on Earth.
Yeah.
Think massive machines, huge complexity.
Billions upon billions chasing this dream that, let's be frank, hasn't delivered on its promise yet. Not even close, really.
Not even remotely close to commercial power. But then here's the kicker, the real mind blower we need you to grasp right now.
Get ready for this. Back in 1989, two scientists, Martin Fleischmann and Stanley Pons, stood up at a press conference.
And they basically announced they'd cracked it. Clean, limitless energy, virtually free power.
How? Not with a billion-dollar reactor.
Yep.
No, they claimed they did it with, essentially, stuff you could find in a well-stocked chemistry lab. A jar, some special water, a bit of metal.
Yeah, just water and metal on a tabletop. And that claim, it wasn't just revolutionary. It was a direct threat, an existential threat to the entire energy establishment, to the physicists building those giant machines.
And the reaction wasn't just skepticism. Our sources argue it was an immediate, orchestrated campaign to bury it, to destroy it.
Which is why today, our mission is to unpack this whole incredible story. We're digging into the original cold fusion discovery, the radical physics it suggests.
The alleged cover-up, which got nicknamed Heavy Watergate, which is just incredible in itself.
Right. And the truly mind-bending implications, if this is real. Imagine a future where energy isn't controlled by massive corporations, where it's decentralized, personal.
It changes everything. But first, let's set the stage properly. You need to understand the sheer scale of what they were up against. Hot fusion research.
Oh, yeah. Think ITER, the international project in France. We're talking a Tokamak reactor projected to cost maybe $5 billion, maybe more now, who knows. The total long-term U.S. effort to get any hot fusion tech to commercial viability. Estimates hover around $18 billion.
$18 billion. And these machines, they are colossal. They need the energy output of a small town just to power up the magnets and systems required to contain plasma heated to millions of degrees Celsius.
Millions. Trying to replicate the core of the sun. And after all that, decades of work, billions spent. What's the record energy output?
This is almost painful to say. The world record for sustained fusion energy generation from one of these behemoths, 6 megajoules.
6, which sounds like a lot, maybe. But put it in perspective. 6 megajoules is enough energy to power a single standard 60-watt light bulb for, what, about 28 hours?
Less than a day and a half of light. From a multi-billion-dollar machine, that's the benchmark.
Keep that number, 6 megajoules for $18 billion, firmly in your head.
Because now we dive into part 1. Prepare yourself because your power bill might just be a scam.
Okay, let's go back. March 23rd, 1989, University of Utah, Fleischmann and Pons make their announcement. Controlled nuclear fusion at room temperature.
It sounds like science fiction, right? But the setup they described was shockingly simple. That's what made it so terrifying to the establishment.
It was basically an electrolytic cell. Think of a glass jar. Inside, they put heavy water. That's just water where the normal hydrogen is replaced by deuterium, a heavier isotope of hydrogen.
Okay, heavy water. Got it. What else?
They added a lithium salt, LiOD, to help conduct electricity, and then the electrodes. A platinum wire as the anode, the positive side.
And the cathode, the negative side.
That was the magic ingredient. A rod made of palladium.
Yeah.
P'd on the periodic table. It's a rare, silvery metal known for one very weird property.
We'll get to that property later, I bet. So they had this jar, heavy water, salt, platinum, palladium. What did they do?
They just ran a small electric current through it. For weeks, sometimes months, letting the deuterium from the heavy water soak into the palladium.
And the result wasn't just some interesting chemistry experiment bubbling away.
Not even close. The claim was anomalous heat, excess energy. They'd have the cell running steadily, say at 30 degrees Celsius, drawing a known low amount of input power.
Right, just baseline temperature.
Then, suddenly, unpredictably, the temperature would surge. It might jump to 50 degrees Celsius or even higher, and it would stay there for days, sometimes weeks.
With no extra electricity going in.
Exactly. The input power stayed the same, but the output power, the heat coming off this little jar, was massively higher. This wasn't a battery effect. It wasn't stored chemical energy being released. It defied explanation by chemistry.
How much energy are we talking about? You said massive.
We're talking thousands of electron volts per atom in the palladium rod. That's nuclear level energy.
Yeah.
Our sources stress the scale here. They measured Hundreds of megajoules coming out of just 1 cubic centimeter of that palladium rod over maybe 3 months.
Okay, hundreds of megajoules per cubic centimeter. How does that compare to, say, braining something?
Well, the absolute maximum energy you can get from the most potent chemical reaction in that same volume, like an explosion, is about 0.05 megajoules per cc.
0.05 compared to hundreds.
Yeah. We're talking thousands of times more energy than any chemical process could possibly produce. Thousands.
That's staggering. Where could that energy possibly come from?
There was only one plausible explanation they could offer. It had to be a nuclear process. Fusion.
Yeah.
Happening right there in the jar.
They claimed the energy density of the heat output per volume was comparable to the core of some nuclear fission reactors, like the ones in power plants.
Comparable heat density to a fission fuel rod. But, and this is the absolute key part, without the deadly penetrating radiation you always get with fission. No massive shielding needed, apparently.
So you've got fission-level power density potentially from a simple device without the dangerous byproducts. You can see why this was perceived as an immediate existential threat.
Oh, absolutely. Think about it. This little tabletop device, if scalable, could potentially replace the need for the estimated $4 trillion in future U.S. power plant construction planned at the time. $4 trillion wiped out.
By a chemistry experiment you could maybe replicate in a high school?
That was the promise and the terror, taming the power of the sun or something like it in a test tube.
And this wasn't just gentle, controllable heat they were dealing with either, was it? There's a pretty dramatic story from their earlier work.
Yeah, there is. Around 1985, before the main announcement, one of their early cells apparently exploded one night, violently.
How violently?
Violently enough to destroy part of the fume hood it was in, shatter the glassware, and gouge a 4-inch chunk out of the solid concrete floor beneath it.
A hole in the concrete from that little cell.
That's the report. They suspected it was a literal fusion ignition, a runaway nuclear event. The kind of energy release you just don't get from chemistry.
Which explains why they later included warnings in their papers about potential explosion hazards. They knew they were playing with something incredibly powerful, possibly dangerously so.
Right. It wasn't just a gentle simmer. It had the potential for significant bangs.
Okay, so let's recap. Simple device. Palladium rod, heavy water, produces thousands of times more energy than chemistry allows. Comparable power density to fission fuel rods. Potential for explosions. And this is all happening while the official $18 billion hot fusion effort is struggling to get 6 megajoules.
That's the picture.
Yeah.
The contrast is just stark.
So the unavoidable question is, how? How could fusion, which needs millions of degrees to overcome the natural repulsion between atomic nuclei, possibly happen in a room temperature jar of water? Physics says it shouldn't.
That is the question, isn't it? And the answer, according to the proponents, lies in the metal itself. This takes us straight into part 2, the solid-state secret.
All right. Why is fusion normally so hard? Let's start there.
Okay, basic physics. Atomic nuclei, like deuterium nuclei, which are just a proton and a neutron, are positively charged, like charges repel violently. It's called the Coulomb barrier.
It's like trying to push the north poles of 2 strong magnets together. They just refuse.
Exactly. To get them close enough for the strong nuclear force, the force that holds nuclei together, to take over and fuse them, you need to slam them together with incredible energy, overcome that repulsion.
And how do you give them that energy in conventional fusion?
Brute force heat. Millions of degrees Celsius, like in the sun or inside those Tokamak reactors. The heat makes the nuclei move so incredibly fast they have enough kinetic energy to sometimes tunnel through or smash through that Coulomb barrier.
Ramming speed, basically.
Pretty much. Now, there was another idea around at the time for cold fusion, muon-catalyzed fusion. Stephen Jones, who was also working at BYU near Utah, was involved in that.
Right, I've heard of that, using exotic particles, muons, to kind of shield the nuclei.
Exactly. And it worked. They proved fusion could happen at room temperature using muons. But the problem was, it wasn't commercially viable. You couldn't get more energy out than you put in to create the muons. Interesting physics, but not an energy source.
Okay, so muon fusion was a dead end for power, but Fleischmann and Pons weren't using muons, they were using palladium.
Correct. Their approach was totally different. No particle accelerators, no muons, just solid matter. This is the radical departure, the solid-state secret.
So what's the secret? How does the solid palladium help?
Remember, I mentioned palladium has a weird property. Its unique ability to act like a sponge for hydrogen isotopes, like deuterium. It can absorb huge amounts, up to 900 times its own volume of deuterium gas into its crystal lattice structure.
900 times, that's a lot. It packs them in really tightly.
Incredibly tightly. Inside the rigid, repeating structure of the palladium metal crystals, the deuterium nuclei, called deuterons, are forced into very close proximity under immense effective pressures.
So the metal lattice itself is squeezing them together, like a subatomic vice.
That's the core idea. This metal lattice acts as a prison, holding the deuterons close. But it does more than just squeeze. Researchers theorize that the environment inside the metal lattice fundamentally changes the rules.
Changes the rules of physics. How?
The theory is that the dense cloud of electrons naturally present in the metal, combined with the regular structure of the lattice, provides intense screening. It effectively weakens or shields the positive charge of the deuterons from each other.
So it lowers that Coulomb barrier we talked about, makes it easier for them to get close.
Exactly. Or maybe even bypasses it in some novel way. Pons himself described the conditions inside the palladium as a kind of low-temperature plasma inside the metal. It's not about high kinetic energy from heat. It's about using the unique quantum mechanical environment of the solid state to enable fusion.
Okay, that's a pretty radical concept. The metal itself facilitates fusion.
Deeply radical. It flew in the face of accepted nuclear physics. But it also offered an explanation for the other massive anomaly they observed. The lack of deadly radiation, the aneutron anomaly.
Right. You mentioned that, and conventional fusion should produce nasty stuff.
Yeah. If you fuse two deuterium nuclei, D plus D fusion, there are two main outcomes, roughly 50-50 probability. One produces tritium, another hydrogen isotope, plus a proton. The other produces helium-3 plus a high-energy neutron.
And neutrons are bad news, right? Penetrating radiation makes things radioactive.
Very bad news. That neutron carries away a lot of energy and requires heavy shielding. If Fleischmann and Pons were getting fusion at the rates needed to produce the heat they saw, the neutron flux should have been instantly lethal. But it wasn't there.
They measured neutrons, didn't they? Just not nearly enough to account for the heat.
Exactly. They detected some neutrons, and later experiments confirmed low levels of tritium, indicating some conventional D plus D fusion was happening. But the levels were millions, maybe billions of times too low to explain the massive excess heat being generated.
So if it's fusion, but it's not making the expected radiation, where is all that nuclear energy going? It has to go somewhere.
This is where the theories got even more interesting, involving the lattice again. People like MIT's Peter Hagelstein and even Nobel laureate Julian Schwinger proposed mechanisms where the fusion energy, instead of being released as high-energy particles, gets directly and harmlessly dumped into the palladium lattice itself, absorbed by the structure.
How? Like the lattice acts as a perfect shock absorber.
Kind of. Hagelstein talked about coherent fusion, where the energy excites collective vibrations in the crystal lattice things called optical phonons. Think of it like the energy shaking the entire lattice structure in a coordinated way, generating heat instead of radiation.
So the energy comes out as heat, lattice vibrations, not flying particles.
That's the idea. Schwinger proposed a different mechanism involving the production of helium-3, where the huge chunk of energy, like 5.5 MeV of gamma-ray energy that should have come out, was somehow instantaneously transferred to the lattice. Other models based on statistical physics also emerged.
Statistical physics, how does that fit in?
The argument there is that in a complex many-body system, like a crystal lattice loaded with deuterium, the system will naturally favor pathways that maximize entropy production. Producing stable, unexcited final products, like helium-4, which was also claimed later, and releasing the energy as gentle heat is a much higher entropy, more probable outcome than producing highly energetic, unstable particles like neutrons.
Wow. So the physics is suggesting the solid state itself prefers a clean nuclear reaction.
That's the interpretation. The lattice isn't just a cage, it's an active participant, fundamentally changing the outcome of the nuclear reaction. It tames the fusion fire.
Okay, this solid-state secret is pretty mind-bending, but there must have been huge skepticism. How did they try to prove it wasn't just some weird chemical effect or measurement error?
Oh, the skepticism was immense, and proving it definitively was tough, especially with reproducibility issues early on. But one phenomenon really stood out as impossible to explain chemically.
What was that?
The heat after death phenomenon.
Heat after death. Sounds dramatic.
It was. Professor Yoshiaki Arata in Japan, working with specially designed cathodes, palladium nanoparticles packed inside a palladium casing called double structure, or DS cathodes.
Okay, more advanced than the simple rods. Nanotechnology involved.
Right. Arata and others demonstrated conclusively that these cells continue to produce significant excess heat for hours, sometimes even days, after the input electrical current was completely shut off.
Turned off completely.
Completely off. No electricity going in, but the cell just kept pumping out heat.
That just blows away any possibility of it being an electrical measurement error or some kind of resistance heating effect, doesn't it?
Absolutely. If the power is off, any electrochemical reaction should stop almost instantly. But these things kept going. There's a famous account from another researcher, T. Mizuno.
Yes.
His cell got so hot after being turned off, he had to put it in a container of water just to cool it down, and it kept producing heat, boiling off the water. Over 11 days, it evaporated 37.5 liters of water.
37 liters, just sitting there, turned off. How much energy is that?
That evaporation represents about 85 megajoules of energy, released after the power was cut.
85 megajoules. Let's go back to our benchmark. The $18 billion Tokamak record was 6 megajoules. This dead cell produced over 14 times that amount.
While sitting passively in a bucket of water, yes. That kind of sustained energy release with zero input power simply cannot be chemistry. It had to be drawing on some stored internal energy source, and the only source dense enough is nuclear.
That heat after death seems like a smoking gun, undeniable proof of something extraordinary.
It was seen as incredibly strong evidence, and it also helped explain the reproducibility problems.
How so?
Because it suggested the effect depended on creating very specific conditions inside the palladium, these nuclear active environments, or NAEs. Nanoscale regions, or defects, where the deuterium loading, pressure, and electronic conditions were just right for fusion.
So the early experiments were hit or miss because they relied on randomly forming these perfect microscopic spots in the metal.
Exactly. It was luck of the draw with the material preparation. The heat after death suggested that once these NAEs were formed by the initial electrical loading, the internal stresses could maintain them for a while, even without power, allowing the reaction to coast.
Which led researchers to think, okay, instead of relying on luck, let's engineer these NAEs.
Precisely. That's why the field quickly shifted towards materials, science, and nanotechnology, designing materials like Arata's nanoparticles or using nickel-based alloys and composites specifically structured at the nanoscale to reliably create these active zones.
So the focus became creating the right solid-state environment deliberately rather than hoping for it.
Right. And the fact that engineering these nanoscale environments works, that it improves reproducibility and enhances the effect, further confirms that this is fundamentally a condensed matter, solid-state nuclear phenomenon. It's not just some fluke.
Okay, so we've got a plausible, if radical, theory based on solid-state physics. We've got experimental evidence like heat after death that seems irrefutable. The potential is world-changing. What happened next should have been Nobel Prizes, right? Global research programs.
You would think so. But what happened instead was, well, it was brutal. An organized scientific takedown.
Which brings us perfectly to part 3, Heavy Watergate, the scientific cover-up. This is where the science meets some very harsh real-world politics and allegedly dirty tricks.
Get ready, because this part of the story is frankly disturbing. The Utah announcement wasn't met with cautious optimism or even healthy skepticism. It was met with immediate, intense, and seemingly coordinated hostility.
Especially from certain quarters.
Particularly from the established hot fusion research community. Physicists, especially plasma physicists, working on those big Tokamak projects. Our sources are clear. They saw cold fusion not as an interesting possibility, but as a direct threat.
A threat to their funding, their careers, their entire field.
All of the above. If a simple tabletop device could do what their multi-billion-dollar machines couldn't, the funding pipeline for hot fusion could dry up overnight. The stakes were incredibly high.
But surely there were some who tried to replicate it, some early confirmations.
There were, almost immediately. Texas A&M University reported confirming excess heat. Researchers at Moscow University claimed they detected neutrons in 20 separate experiments, commenting on how surprisingly simple the setup was. Lajos Kossuth University in Hungary also reported positive results.
So the effect was being seen by others, quickly.
Yes, but those early confirmations were largely drowned out by a wave of high-profile negative results and dismissals, often from very prestigious institutions.
And the most prominent, most controversial campaign came from?
MIT. Specifically the MIT Plasma Fusion Center, or PFC. This is the heart of the heavy Watergate allegations, claims of deliberate scientific misconduct, data manipulation, and media manipulation aimed at killing cold fusion.
Who are the key players there?
The leaders of the MIT effort were Dr. Richard Petrasso and Professor Ronald Parker, the director of the PFC at the time. Their team moved very quickly and very publicly to debunk the Utah claims.
What did they focus on?
Initially, they focused heavily on the neutrons, or rather, the lack of neutrons compared to the heat. They challenged Fleischmann and Pons' original gamma-ray measurements used to infer neutron production, arguing it was just an instrument glitch or artifact.
Okay, so they attacked the radiation measurements first.
Yes, and they were largely successful in convincing the mainstream scientific community and the media that the F&P neutron claims were wrong. They framed cold fusion as an aneutronic process, meaning few or no neutrons.
But wait, as we discussed, if it's clean energy, being aneutronic should be a good thing, right? Less radiation?
Logically, yes. It should have supported the idea of a novel, clean nuclear process. But that's not how MIT framed it. They used the lack of neutrons as proof that no nuclear reaction could be happening at all, because conventional fusion must produce lots of neutrons.
Ah, I see. So they used the lack of the dirty byproduct to dismiss the entire phenomenon, even the heat.
Exactly. They conflated no neutrons with no fusion, effectively ignoring the massive excess heat that was the primary claim. Their public stance became, no significant heat, no significant neutrons, therefore cold fusion is junk science or pathological science.
That's a very strong condemnation from a place like MIT. But were there questions about how they reached that conclusion?
There were massive questions, raised most forcefully by Dr. Eugene Mallove.
Who was he?
Mallove was an MIT science writer, an alum who was initially tasked with writing about the MIT cold fusion experiments for the Institute's news office. But what he uncovered led him to resign in protest and become arguably the most vocal critic of the MIT group, alleging outright fraud.
Fraud, that's a heavy charge against MIT. What was his evidence?
Mallove documented several key things. First, the attitude. He obtained a tape recording of Professor Parker talking to a Boston Herald reporter, Nick Tate. On the tape, Parker explicitly calls the Utah work scientific schlock and a scam.
Wow, he said that.
He did. Later, Parker publicly denied using those specific words, but the tape existed. Mallove argued this showed a clear bias and intent to debunk from the start.
Did Parker give a reason for this hostility on the tape?
Yes, and it was telling. Parker was recorded saying something like, when you're asking for $125 million for the university, you have to draw the line. Mallove interpreted this as a direct admission that protecting MIT's funding, particularly for hot fusion, was a major motivation.
Okay, so bias and motivation, but what about the actual science? Did Mallove claim they manipulated data?
He did. This is the most serious allegation. Mallove, later working with another researcher, Dr. Mitchell Schwartz, meticulously analyzed the raw data and draft reports from the MIT PFC's second phase of calorimetry experiments, the ones measuring the heat.
And what did they find? Or claim to find?
They claimed they found evidence that the data presented in the final published report had been improperly altered from the earlier drafts to eliminate signs of excess heat.
Altered?
They focused on the comparison between the heavy water cell, where cold fusion might occur, and the light water control cell, where it shouldn't. Mallove and Schwartz argued that in the draft reports, the power curve for the heavy water cell showed a small but persistent positive signal, maybe tens of milliwatts, of excess heat. It was dominantly above the zero line.
Okay, a small positive signal. What happened in the final report?
In the final published version, that heavy water curve had been mathematically shifted downwards, just slightly, but enough so that it no longer showed any significant excess heat, and instead perfectly mirrored the null result from the light water control.
Shifted? You mean they just adjusted the baseline?
That was the accusation, that an arbitrary data processing step was introduced between the draft and final version specifically to make the potentially positive result disappear and ensure definitive null finding. They essentially zeroed it out.
If true, that's not skepticism, that's cooking the books.
It's the definition of scientific misconduct, according to Mallove. He argued MIT didn't just fail to find cold fusion, they actively manipulated their data to make sure they wouldn't find it, likely to protect their institutional interests.
How did the broader scientific community react to these allegations and the MIT report?
The MIT report, being from such a prestigious source and declaring a strong negative result, carried enormous weight. It was heavily influential in shaping the official narrative. The Department of Energy convened a panel in 1989, the ERB panel.
And their conclusion?
Largely skeptical, heavily influenced by the negative reports like MIT's, and again, according to critics, by the ingrained skepticism and funding fears of the hot fusion physicists on the panel. They concluded there wasn't compelling evidence and recommended against any special funding for cold fusion research.
So the door was basically slammed shut. Officially.
Pretty much. The field was effectively blacklisted in the U.S. mainstream. It became career suicide for many academics to touch it. The censorship was intense.
Censorship? How so?
Journals refused to publish positive papers. Conferences refused to host sessions. It reached the point where even Julian Schwer, a Nobel Prize-winning physicist who developed a theory for cold fusion.
Yes, we mentioned him. What happened?
He famously resigned from the American Physical Society, APS, in protest. He felt the organization's leadership was actively suppressing debate and refusing to even consider papers on the topic, including his own theoretical work.
A Nobel laureate resigning because his work was being censored by the main physics body? That's extraordinary.
It shows how deep the hostility ran. It wasn't just disagreement. It was organized suppression, according to these sources. Heavy Watergate, indeed.
Okay, this story is it's deeply unsettling. Thinking about how science is supposed to work versus how it apparently did work in this case, according to these accounts. If you're finding this as fascinating and frankly as concerning as we are, and you believe it's crucial to support channels that dig into these controversial topics the mainstream often ignores,
then please take a moment right now. Hit that like button, subscribe to the channel, maybe even consider joining our memberships if you can. Your support directly enables us to keep doing these deep dives, bypassing the usual gatekeepers, and bringing you the stories that others might want to keep hidden. It genuinely makes a huge difference.
It really does. Okay, so mainstream science, fueled by reports like MIT's, declared cold fusion dead and buried by late 1989, early 1990s. But was it really dead?
Not by a long shot. Like any truly compelling idea with potentially revolutionary implications, it refused to die. But research didn't stop, it just went underground or overseas.
Which brings us to part 4, the unkillable truth and the democratization of energy. So where did the research continue?
All over the world, actually, just often quietly. India maintained a significant program at their Bhabha Atomic Research Center, BRC. Japan became a major hub, with researchers at places like Tohoku University, Hokkaido University, and later private companies like Clean Planet Inc. making big strides.
What about Russia?
Russia, too. Figures like A.G. Parkhomov became known for replicating and extending some of the later nickel-hydrogen LENR experiments. And even within the U.S., research quietly persisted.
Didn't the U.S. Navy maintain some interest?
Yes, that's a crucial point. Researchers at the Navy's Spare Systems Center in San Diego continued low-level work for years, publishing peer-reviewed papers on excess heat, transmutations, and radiation detection. People like David Nagel, a prominent Navy scientist, argued publicly that the phenomenon was real and deserved serious funding, given the obvious defense implications.
So the military saw the potential, even if civilian science funding was blocked.
It seemed so. And private industry didn't completely give up either. Smaller companies, venture capitalists, outfits like Reading Energy, Atlantic Energy, later others like Blacklight Power, though their theory is different, kept investing, hoping to crack the code and reap the rewards. The lure of limitless clean energy was just too strong.
And eventually, did the official stance in the U.S. start to thaw?
It took decades, but yes. The sheer weight of accumulated positive evidence from labs worldwide, particularly the improved reproducibility using engineered nanomaterials, became harder and harder to ignore. The internet also played a role, allowing suppressed researchers to share findings globally.
And the big turning point.
A landmark moment came in 2021. The U.S. Department of Energy's Advanced Research Agency, ARPAE, announced a $10 million program specifically dedicated to funding low-energy nuclear reactions, LENR research.
$10 million, after decades of dismissal.
Exactly. The program's explicit goal was to break through the knowledge impasse. It was essentially an official admission from the U.S. government that, okay, maybe there really is something here after all, and we need to understand it.
That's a huge reversal. So the U.S. government is back in the game. But what exactly are they and the international researchers finding now? Is it still just about excess heat?
Oh, it's gone way beyond just heat. The findings have become even more bizarre, more radical. We're talking about confirmed evidence of nuclear transmutation. Alchemy.
Alchemy, like turning lead into gold? Seriously.
Well, maybe not lead into gold yet, but definitely creating entirely new elements inside these LENR reactors. Elements that simply weren't there to begin with.
How did they know?
By carefully analyzing the composition of the electrodes, the palladium or nickel before and after running the experiments for extended periods, they use highly sensitive surface analysis techniques.
And they find new elements have appeared. Which ones?
The lists published in peer-reviewed papers are stunning. They include significant amounts of calcium, vanadium, titanium, manganese, iron, cobalt, copper, zinc, gallium, even heavier elements like strontium, barium, ytterbium, even, get this, hafnium.
That's way down the periodic table. How could you possibly make hafnium from palladium and deuterium?
That's the trillion-dollar question. According to standard nuclear physics, you can't. Not in a low-energy environment. You'd need the kind of energies found in supernovae or particle accelerators to fuse that many protons and neutrons together or do complex fission capture processes.
So what are the theories? How could this alchemy be happening?
The theories are still developing and highly speculative, but they generally involve multi-body fusion reactions or complex interactions mediated by the lattice environment. It's not just simple D plus D fusion anymore.
Give me an example.
One really wild hypothesis proposed to explain the appearance of iron, for instance, suggests that somehow 6 protons from the deuterium or maybe even regular hydrogen in the water, 3 oxygen nuclei from the water molecules themselves, and 4 electrons might combine within the lattice environment to form an iron nucleus.
6 protons, 3 oxygens, 4 electrons. Makes iron. That sounds completely impossible by today's physics.
It absolutely breaks the standard model of nuclear reactions. It implies that the weak nuclear force, which normally governs radioactive decay, might be playing a much more active role within the unique conditions of the lattice, somehow allowing protons and neutrons to rearrange themselves into stable, heavier nuclei, bypassing the Coulomb barrier entirely for these complex constructions.
So the lattice isn't just enabling D plus D fusion. It might be acting as a kind of catalytic converter for nuclear matter itself, a transmutation engine.
That's one way to think about it. A silent, powerful particle assembler, creating new matter from basic building blocks in a way we simply don't understand yet.
The implications of that, if you could control it, are just astronomical. Forget energy. You could potentially synthesize rare materials on demand.
Precisely. But let's stick with the energy implications for now, because they alone are enough to shatter everything we know about our civilization. If LENR can be reliably scaled.
Yes. What's the ultimate vision here?
The ultimate implication is that energy stops being a scarce, controlled commodity. It becomes, as some sources put it, a free good like air and water.
How? Because the devices could be small and the fuel cheap?
Exactly. We're not talking about giant power plants anymore. The vision is for small, self-contained energy cells. Maybe the size of a car battery, maybe eventually the size of a pacemaker. Safe, producing heat or electricity directly, fueled by tiny amounts of deuterium extracted cheaply from water.
A personal power source for every home, every vehicle, every device.
That's the dream. Decentralized power. No need for a vulnerable, expensive electrical grid spanning continents. No need for pipelines or supertankers carrying fossil fuels. Power generation becomes local, personal, and virtually free once the device is manufactured.
What would that do to the current energy industry, the oil companies, the utilities?
It would create an economic tsunami unlike anything in history. The centralized energy monopolies that have dominated the world for 150 years would simply evaporate. Why buy expensive gasoline or pay a massive electricity bill if your house and car run for years on a thimbleful of heavy water?
The sources predict oil would be the first casualty.
Yes, because it's the most expensive and logistically complex fossil fuel. The incentive to switch to a near-free, clean, high-density LENR source would be overwhelming. Think about it. Heating and cooling your home year-round for pennies. Driving your car tens of thousands of miles between refueling, maybe only needing a fuel top-up during routine maintenance.
And the cost of the fuel itself, the heavy water.
It would plummet. Right now, heavy water production is energy-intensive. But if you power the separation plants with cold fusion energy, the cost drops dramatically. Maybe $100 a kilogram, maybe even less if it's recycled within the device. It becomes trivially cheap.
So the entire economic structure based on controlling energy resources just collapses.
Overnight. Central power plants, hydroelectric dams, they become obsolete relics. It wouldn't even be worth repairing the transmission lines when every building generates its own power. It's total disruption.
Which leads us to our final thoughts. This journey started with a simple experiment in Utah, plunged into decades of controversy and alleged suppression.
But the core phenomenon, this anomalous energy release, and now even nuclear transmutation within solid matter, just wouldn't die. It survived, went global, got refined through nanotechnology.
And now, even the U.S. government, after decades of hostility, is officially acknowledging it's real enough to fund again. The genie might finally be starting to peek out of the bottle.
So here's the truly provocative thought to leave you with. Forget the $20 billion lie for a moment. Look forward. If these battery-sized LNR devices become reality, powering everything from homes to cars to maybe even implants.
What does that world actually look like? When energy, the fundamental driver of civilization, is no longer scarce or controlled, but abundant and ubiquitous, almost like oxygen.
And if the alchemy aspect is real, if we can truly transmute elements in these small devices, is the biggest revolution not even energy, but the ability to manipulate matter itself at the nuclear level, cleanly and cheaply?
If the power plant fits in your hand, and maybe the element factory too, what other structures of modern society, our economies, our geopolitics, our very understanding of resources simply cease to make sense?
What will humanity actually do with that kind of power? Limitless energy, potentially limitless materials. It's both utopian and maybe a little terrifying to contemplate. And perhaps the most critical question of all.
Who gets to decide how we use it?
That's the future, potentially waiting in the wings, born from a humble experiment and decades of struggle against the tide. The unkillable truth of LNR might just change everything.
Explore the ongoing work. The story is far from over. Thank you for joining us on The Deep Dive.